Good afternoon, folks, and thank you for sticking around on Wednesday afternoon. My name is Bruce McDougall. I'm a solutions systems architect for Cisco, which means essentially I'm a few rungs down the ladder from Cisco Fellow, but I'm here as a substitute speaker for Clarence, whose flight got canceled, so he's unable to attend. Clarence sends his regrets. So, with that said, this is SRv6 update. Technology, deployment, and use cases. First, we wanted to acknowledge partners in this effort over the last couple of years. We've been working with several lead operators, and it's been a terrific partnership. We really appreciate their feedback and their embrace of the technology. We've also been working with an expanding set of ecosystem partners. So this is a set of hardware vendors that have invested in segment routing and SRv6 implementations in their equipment, as well as a number of academic and open source partners that have made investments in segment routing in some applications and open source tools. Finally, a thank you to the Cisco segment routing team for all their hard work over the last couple of years. We did want to mention that an extended recording of this presentation will be available at segmentrouting.net. It should be posted either later today or tomorrow. So with that said, into the presentation itself, a little bit of background review. SR-MPLS, segment routing MPLS, has become kind of the de facto IPv4 solution, and we've seen wide deployment and acceptance around the world. Segment routing is deployed across different market segments. We see implementations and deployments in service provider, web, and enterprise. And the bunch of logos at the bottom of the slide are here to illustrate just a few or a selection of the publicly announced implementations. We figured this is actually kind of tip of the iceberg, as these are just publicly announced deployments. So, but the talk to focus on SRv6. SRv6 is SR for IPv6. And the philosophy of segment routing from the very beginning has been simplicity and to simplify the stack. SRv6 builds upon this simplicity that we got from SR-MPLS. With SR-MPLS, the operator is able to remove the need for LDP and RSVP. With SRv6, we also see the ability to start to remove other protocols and in the control plane stack. SRv6 as an end-to-end IPv6 data plane offers the ability to move away from all of the encapsulation stitching that occurs when IPv4 or when IP fabrics bump into MPLS fabrics. It allows for the removal of inter-AS option A, B, and C kind of stitching, even the MPLS data plane. And then SRv6 based overlays allow for moving away from kind of the cluster of different IP overlays represented by like IP over UDP, VXLAN, and even network service headers. So with SRv6, we get all of this potential simplification and a great deal of scale over V4 or over MPLS. In addition to all that scale, we're finding with the SRv6 network programming paradigm that we also see a significant, like a big bump in functionality. So the SRv6 ecosystem that we've been working with, and I should note that it's a growing ecosystem, it's moving fast. Since about 2017, in March 2017, were the first sort of meetings with the lead operators. And in under 2 years, we went from those initial meetings to actual announcements of commercial deployments in production at the beginning of 2019. Then throughout the year 2019, that grew to 8 commercial deployments. Additionally, in 2019, we saw announcement of 18 line rate hardware implementations and announcement of 11 open source applications, or segment routing being developed and supported in a number of different software tools and apps. We expect this, certainly the list, to grow in 2020 and beyond as well. We wanted to highlight 2 of those operators that announced commercial deployments, SoftBank and Iliad. SoftBank was the very first announcement in January of 2019, and segment routing deployed in production. And then Just a couple weeks later, Iliad, an operator in Italy and France, made an announcement that they had deployed a nationwide SRv6 network using both Cisco equipment as well as their homegrown Iliad node boxes. And these are their cell site routers, where they actually implemented SRv6 within their own network operating system. A quick logo slide on the ecosystem. At the center of the logo slide is actually a little picture from an interop that SIGCOMM did, I think in late 2017 maybe. SRv6 is a proposed standard, so RFC 8402 has been allocated. 8402 defines SRv6 with key concepts such as SRh and SRv6 SIDs. The SR extension header, or SRh itself, is the SRv6 data plane encapsulation, and that one is through IETF last call and is awaiting its RFC number assignment. Also within the Spring Working Group, there are another 3 drafts that are working their way through. They're at last call status now. So the network programming draft, the SRv6 extensions for ISIS, and SRv6 OAM. Very quickly, just to show, this is more for reference later if anyone's interested. There are several iOS XR platforms that have shipping SRv6 feature set today. Same with in the data center, Nexus 9000 has shipping SRv6 feature set. SRv6 reminder, this is actually a quick review of SRv6 network programming. So SRv6 network programming essentially takes, the idea of the 128-bit destination address or the 128-bit, say, SIDs that are in the SRH that follow the outer header. Each of those 128-bit SIDs can represent a 128-bit program or instruction set. So those instruction sets can be found in the outer destination address is the first instruction. And then if needed, there could be additional instructions in the SRH, second instruction, third instruction, and so on. And a little too fast there. Several of these network program instructions are actually codified in the network programming draft. So they've defined, say, some traffic engineering and fast reroute and VPN instruction sets. I think there's a couple other drafts that are in the works out there as well for additional SRv6 network programs. And we think there's an entire ecosystem of network programs that could emerge here in the next couple of years. The SRv6 header, a very quick overview of what it looks like. So the actual outer IPv6 header, source and destination address are at the top. And then after that, the SRH begins itself. And the outer tag is essentially a space for defining group-based policy. The next field is segments left, and that basically just tells us where we are within the program, within the locator stack. And then finally, or within the SID stack, sorry. The SID list itself, or the set of SIDs, each 128-bit SID can be broken or thought of as 2 pieces. There's the outer piece, which is a locator, and then the last bits, which are a function. So a locator is going to tend to be like essentially advertised and bound to a loopback address on a router, and then the function is some sort of like either like a traffic engineering or a VPN or some other kind of function that is completed or that are the last bits of the 128. Then we've got also at the end of the SRH is the metadata TLV, which is basically a optional unspecified size, but this is a place where one could embed any sort of essentially metadata, performance data, for instance, other kinds of data. And that piece we would expect to be processed by like software tools and the like after the routed network has finished sort of moving the traffic through. So I'll just jump to the next. SRv6 routed domain itself. This is to just kind of illustrate sort of packet flow as traffic traverses from a customer through a SRv6 encapsulated domain, say like a service provider network. So this could be an SRv6 VPN. So at domain ingress, let's say customer packet arrives at PE router 1, and it could be an IPv4, could be v6, or even a layer 2 frame. It gets encapsulated in SRv6. The outer IPv6 header includes a list of SRH, say list of segments. Now in this case, it could just be an outer IPv6 header if there's no need to execute any kind of additional service on this packet. Or it could actually have the SRH if we're doing both, say, VPN and traffic steering. So the packet is going to just traverse the blue network here, and it's going to just take IPv6 best path, or the ISIS best path to the egress point, unless we've actually specified something in the network program that says it should steer. It's going to arrive at the egress node, and the egress node itself is going to pop. It's going to read itself as the location or the locator, and read the function as the pop function for whatever VPN it's executing in this case. So it removes that header and forwards on the original packet. And we did want to emphasize that the end-to-end integrity of the actual customer packet. So the SRv6 network itself is not changing the customer packet in any way. It's behaving exactly like an MPLS VPN in this sense, where it's simply encapsulating it in a v6 header, sending it on, and then decap. So we've got actual deployed use cases here to discuss. This one, and just from a terminology perspective, VPN over best effort 5G slice, this could also just mean like MPLS VPN or the equivalent of a layer 3 VPN. Let's say for the network design here, we've assigned the B address space or locator block, and that B address space is associated with the ISIS, just kind of standard best path forwarding. And router 3 is our egress point. So when the packet enters the network at router 1, it's going to encapsulate it in a locator plus a function SRv6 header. So the egress PE node is B3, and then the function is VERF9 in this case. So this is a very simple encapsulation. It's a simple program because we don't need to do anything complex with routing here. We're just IPv6 routing it. So a simple IPv6 header on top, no SRH. So so very little overhead. Jumping past that because it's redundant with this one. The VPN with low delay slice, or just say VPN with an SLA option added to it. So this one comes with a flex algorithm option where, let's say we've defined an alternate ISIS algorithm that says to measure the best path as the lowest delay path. And so we've got, we're measuring, say, link latency on all the links in the network, and then the algorithm itself runs that, and it measures and it determines that the best path from 1 to 3 is at least from the low delay algorithm's perspective, is actually via 2 and then 5. So in this case, we've got another, say, loopback address on the remote router that is assigned an address in the D block. And so we're going to encapsulate this packet because it's got low delay as its service or its SLA. It gets encapsulated in D:3, which is the locator for the low delay path to router 3, the egress node. And then the function, the end of the destination address on that encap is, again, the VERF9 function. So here we get VPN encapsulation and actually low delay traffic steering with a single header and no additional SRH added. And final use case that we're exploring, this is actually consider this, say there's integrated NFV in this path, or it's kind of like it's a service chain essentially, where we've got the same VPN with low delay, but we also want to ship the traffic through some packet inspector or kind of firewall thing somewhere in the middle. So in this case, we have an outer SRv6 header and then a SRH with a single SID, because it's a compound sort of stack here. So the first SRH, and we're still working within the D block because we want low delay. And the first destination address is D:2, and then whatever, the bits to finish out the 128 bits that says send it to this snort node that's hanging off of router 2. The packet comes back after inspection, and the D:3 SID has been promoted to the destination address, and it takes the low latency path from 2 to 3, which happens to be via 5. And so that now that outer destination address, D3 with V9, it behaves just like the previous slide, where when it arrives on egress, we pop and we forward or look up on our within the verse lookup table. Additional, I don't know if this is a use case per se, but this is additional functionality that is really nice with SRv6, and that's load balancing and getting to load balance on a flow label that's right at the front of the packet. So with MPLS, we've got the potential for a deep label stack, and it's hard to actually go. Many hardware platforms are not able to hash on the inner IP after such and such a label stack. So we've got other things like MPLS entropy labels and things like that. And with IPv6, we actually just get flow label out of the box. Like it's part of the protocol. So the ingress PE, as say the customer traffic is coming in, it is hashing on that 5 tuple, and then that PE can essentially mark like a hash index or a hash number in the flow label of the IPv6 encap that it's pushing on those packets. And so as the SRv6 traffic then traverses the downstream nodes, right in front of the header itself is a flow label. So it's able to, so downstream nodes can then hash right on that. And we get this for free with IPv6, so this is terrific. This is a use case. This is kind of, brownfield introduction of the technology use case. So if the network supports plain IPv6 forwarding, then one can introduce SRv6 in that network. So introduction of SRv6 driven, say, VPNs can be done via upgrading the PE nodes that are participating in those SRv6 VPNs. The middle boxes, the P nodes that are in between, they just need to perform v6 forwarding itself. If you wish to implement traffic engineering of some sort or path steering, this doesn't require, say, wholesale implementation of SRv6 across all nodes in the fleet. If a TE objective can be obtained by just enabling SRv6 at certain kind of strategic TE waypoints, that's how it could be rolled out incrementally. I wanted to mention, prior to coming to the dark side, I've worked as a network engineer at a web company and also at a couple service providers. And so I worked with IP networks as well as MPLS networks. And I really like prefix summarization. When working with MPLS networks, we lose prefix summarization, or at least we don't have MPLS ability to summarize MPLS labels. And so we've got, the whole sort of BGP inter AS sort of solution for that. We can stick a BGP LU label in front of, say, a VPN traffic with its transport and VPN label. And that's kind of one of the ways that we scale MPLS networks. With SRv6, though, we automatically inherit IPv6 prefix summarization. So another kind of automatic additional bonus. Let's say we've got a metro with hundreds or even thousands of SRv6 nodes on one side, and we can summarize all of those nodes, say, with a single /48 advertisement that we push into the core. Again, a remote metro, same kind of thing, hundreds or thousands of nodes summarized as a single entry into the core. And so now we could imagine a global network where you've got hundreds or potentially thousands of metros, where you've got hundreds or thousands of nodes, and each one of them is potentially advertising just a single prefix into the core, and your core is, it's got just a couple hundred route entries at that point, or even a few thousand. This is an amazing scaling mechanism, and I just really enjoy prefix summarization. It's a great capability. So, on top of prefix summarization, essentially SRv6 does have excellent native scale. We find that a lot of the use cases, we can support a lot of use cases with a single outer IPv6 header. And then after that, most use cases can be satisfied with one or two SIDs in the SRH. We do get the prefix summarization gain, and really we've got several operators that have implemented in production, and they're happy with what they're getting, and definitely happy to share experience. And because this is network operations, we can't just talk about simplification of architecture without talking about trying to simplify ops as well. The team has built a segment routing or SRv6 NSO kind of automation function pack for the TailF NSO product. So it includes basically all of the capabilities to automate rollout of address allocation, SID allocation, the ability to roll it out multi-domain, to turn on latency measurement and BFD kinds of features, things like that. We also recognize, though, that many operators prefer to build their own automation and management systems. And so at least within our implementation, we're making sure that all of the native Yang data models support SRv6 features as they are added. And we're working with, I know that the Open Config group has at least gotten started on an SRv6 data model themselves. Another quick note on scale. So when it comes to actual address allocation, IPv6 space, so the two operators that we highlight in the talk here, Iliad chose to make use of the private FC/8 space for their SID block allocation. They basically decided to go with a /40 from that FC8 space, which represents less than a billionth of the entire FC8 space. So that's great because they've got room to grow should they need some more address space. SoftBank opted to use their own public v6 space, and they just allocated a /40 from their /20 that they have from APNIC to designate for their SRv6 SID block. So that /40 itself represents just 1/millionth of their address space. All right, so the final piece of this talk, and this is kind of one of the biggest pieces actually, we're introducing SRv6 microprogram. So microprogram is a set of new micro instructions. So if you recall from the network programming paradigm, each 128-bit SID represents an instruction or instruction set, a program if you will. And with microprogram, we look to take that 128 bits and break it into potentially several smaller programs. We want to mention that microprogram also, it completely leverages existing SRH encapsulation and SRv6 control plane, so there's zero extension required to either of the protocols. So a reminder of the network program. The first instruction is the destination address. Second instruction, third instruction, if needed, are the SIDs that follow in the SRH itself. So this is network programming as we first conceived. Now with SRv6 microprogram, basically any of those instructions that we just showed could represent or could hold a microprogram within it. So the first instruction could carry an actual microprogram with it. The second instruction could carry microprogram. And maybe the third instruction actually doesn't. Maybe that's a normal 128-bit network program. Or, alternatively, maybe the outer destination address is a 128-bit network program, but then the second and third SID, maybe those are carrying microprograms within them. So the microprogram itself, how this is constructed, the SRv6 SID itself is 128 bits in length. And let's say, we can break that up into 8 groups of 4 nibbles each, and or 8 groups of 16 bits, if you will. So if we assume an allocation block, we're going to say takes a BB/32 and say this is our microprogram block. And then if we have micro instructions that take place in 4 nibbles, i.e. in 16 bits length, we can build a destination address or a SID that looks something like this, where we've got the first 32 bits are the BB block identifying this packet as having a microprogram instruction set. And then we have 6 chunks of 16 bits that follow that each can execute a SRv6 microprogram. So 6 micro instructions per SRv6 instruction is what this means. So a few slides to kind of walk through how this works. Let's say we've got this network here where we want to send traffic from site A to site B, but we want to send it over a very specific path. We want it to go through router 8, then router 7, then router 2. And with normal SRv6 network programming, this would require an outer destination address to router 8, and then 2 SIDs in the SRH sitting behind for getting traffic to router 7 and then to router 2. Complete building here. So with microprogram though, we can do this easily with a single destination address. We don't need to add additional SIDs. And the way this works, what we do is on ingress, we impose a SRv6 header with a destination address of the first 32 bits are our B block, and then a set of the next 3 16-bit chunks are essentially identifiers that can be stand-ins for the locator to get to router 8, then 7, then 2. So this is the initial outer destination address. And the way that also works is, that 0800 that was came as the next 16 bits, and the 0700 that was the next 16 bits, and 0200. These are all basically loopback addresses on each of those nodes respectively that they're all advertising into ISIS as /48s. So these are all, it's IPv6 routing. So traffic enters the network and gets encapsulated in the microprogram. And initially, we're not doing anything with this program other than following the IGP best path to router 8. So routers 4 and 5 don't even need to be SRv6 aware. All right, so we've arrived at router 8. And this is key, so I'm going to take a drink of water. The shift and forward. Sorry. Packet arrives at router 8, and the destination address that it sees has that 0800 followed by 16-bit sort of microprograms for other routers. It sees itself, though, as 0800, so it's the kind of microprogram locator. What router 8 is going to do with this packet is it's going to take from after the first 32 bits, it's going to take, actually after the first 48 bits, it's going to shift forward 16 bits. It's going to essentially take its locator out of that IPv6 address. So when it shifts it forward like that, we have essentially a new destination address. The last sort of micro instruction set is pushed onto the end of the address. And with SRv6 network programming and microprogram, if the ending bits are 0, that simply signifies end of the program. So now we have a new IPv6 destination address, as we've done a 16-bit shift and forward. So that new address, our router simply does a lookup on the updated destination address, and it has a match for now, the B block 0700/48 that it learned from a normal ISIS advertisement. And so it forwards to that address accordingly. Packet arrives at router 7, and essentially the same process repeats, actually. Router 7 sees that itself, its locator is the address. It's going to take that address, perform a 16-bit shift and forward, so it takes its own self out of that, and then backfill the last 16 bits with zeros. and then it does a lookup on now the new /48, or the newest, longest match, which happens to be a /48, which happens to be the advertisement we got that the entire network got from router 2. So it does the lookup and it forwards accordingly. And then as we go through routers 6 and 3, it's essentially we're back to IPv6 routing at this point. These guys don't have to be SRv6 aware, they're just following their ISIS path to router 2. Router 2 receives the packet fib longest match on itself. It's the locator, and presumably there's the function in those bits after it that say decapsulate and cross-connect to customer at site B. So there we steered through 3 kind of middle hops and executed a VPN use case all within a single destination address, because we're able to use the 16-bit microprograms. So this is really powerful. This is like really scalable, especially for traffic engineering kinds of use cases. We calculate out that with a single 40-byte SRH overhead, you can get up to 18 kind of like microprograms, or steering hops, or potentially like service chain hops out of a single destination, or out of that single 40-byte SRH. So this is mathematically the best SRv6 compression solution. We've also demonstrated it operating at line rate in multi-terabit hardware. This solution is very friendly to merchant silicon. It's trivial for silicon to do address rewrites like this, where every router rewrites a destination MAC address on every packet anyway. So this is really easy for merchant. And then it's also friendly on legacy equipment, in the sense that anything that is not SRv6 aware or microprogram aware, as long as it's an IPv6 router, it's able to forward these packets long. Microprogram comes at no cost. So what we mean by that is it uses the existing network programming model, it uses the existing SRH encapsulation, and it uses the existing SRv6 control planes. So there's no extension required for use of the microprogram. We also, key benefit is the ability to, what we're seeing is, or the ability to actually do the SRv6 and microprogram encapsulation at the host. We know that there are several operators out there that are doing this kind of thing, where encap control happening at the host or hypervisor layer, and this is really powerful because the flexibility that you get with doing encapsulation there is amazing. We have a couple of operators that have done some initial evaluation and testing of SRv6 microprogram. Alibaba first. Dennis Kai, architect at Alibaba, he reports a successful milestone in January, and this is SRv6 microprogram operating at line rate, verified with equipment in the Cisco lab. So this is Cisco 8000 series, NCS 5500, ASR9K. And Alibaba's use case is essentially end-to-end SDN control of a common like IPv6 forwarding plane. So the applications are already enabled, IPv6 enabled, the network is IPv6 enabled. They, as the previous slide described, performing the encapsulation at the host itself within their stack, they control the encapsulation point. And so this gives them a single data plane to operate end-to-end across their network, which is very powerful. Second operator that has successfully tested microprogram, Bell Canada, they tested and demonstrated microprogram operating at line rate in their lab this time. Same set of hardware. Their use case is 5G scale, and to provide data plane simplification, a single encap end-to-end. Their use case also, they have an ambitious use case where they want to do all sorts of integrated traffic engineering, slicing, VPN, integrated NFV, and other stuff. They also describe optimum load balancing as a key benefit, and the ability to run this over a brownfield network as well, to be able to just make use of v6 forwarding. We are in the process of, and I think Jakob has actually completed this interop test. So this is an interop test of microprogram itself. So in a Cisco lab, Jakob Horn did this tested the SRv6 microprogram implementation in Linux and VPP, and also Barefoot Tofino, Jericho 2, Marvell's Falcon, and then several Cisco platforms are involved in this interop. And I think the announcement for it and the publication of it here is going to happen either within this week or next. So to conclude, SRv6, as part of the segment routing family, simplicity is what we aim for. It is the prevailing factor. Looking to have the ability to move to a common end-to-end data plane, a common end-to-end encapsulation for both underlay and overlay technologies could allow us to turn off or eliminate a whole lot of kind of control plane and state and technologies that cause complexity. SRv6 gives us incredible scale, and with the network programming paradigm and microprogram capabilities, also a boatload of functionality. This is all happening fast. We're seeing great uptake, and are really excited about both customer implementations as well as the growing list of hardware and open source implementations. And again, an extended version of this this presentation is recorded and going to be posted here in the next day or two. Final slide, just like some links for references, places to learn more, stuff like that. And with that, thank you very much. Thanks for sticking around late in the afternoon on a Wednesday at the end of the conference. And I think we do have a bit of time if anyone has questions. Yeah.
Yeah, hi. I'm Ideal from Alibaba.
Mm-hmm.
Yeah. I understand that segment routing technology has been already deployed in some ISP service provider network, as well as enterprise, but mainly in their core networks. Do you see any trend to apply this technology into the data center? Or any deployment case
I think SRv6 absolutely could apply in the data center. I think it has a better shot of applying than segment routing itself, because data center fabrics have been IP only for so long. It's very difficult to introduce MPLS and label switching into data center, especially that's like the MSDC kind of data center, scaled data centers. SRv6, though, could absolutely be introduced in data center, and so long as the data center IP fabric is dual stack, I know that at least cloud operators, they control the encapsulation at the host itself within the hypervisor stack. So they could take advantage of SRv6 by just doing the encap at the host and then keeping the data center fabric itself IPv6. So I think it's hugely applicable to cloud operators. Yeah.
Thank you.
Yeah. Any others? Okay. Well, thanks, folks. Appreciate it.